Alright, Mr. Palmer here, going to do a video on big O notation, talking about the time and space complexity of algorithms, okay? So basically, by the end of this video, you should be able to explain 6 big O classifications in relation to how they apply to time and space. The caveat here is I like to program first, and I'm a mathematician second or third, or maybe fourth, fifth, sixth, seventh, eighth, maybe down 10th on the list, okay? So I'm going to do what I can to explain this topic. But you may want to go to your maths teacher and get a heads up on the logarithms, etc. Okay, so 6 classifications of big O I want to talk about. There's a whole bunch of them. Okay, you can look it up on Wikipedia and you can see, and they will go in. If you're deep into the maths, you can go and have a look at it and go and see. Okay, but the first one is O1. Okay, where the time to execute will always be the same. We've got linear complexity, quadratic or polynomial complexity actually, and I'll show you why it's polynomial. Then we've got 2 to the n, okay, exponential, and then we have factorial complexity, and finally logarithmic complexity. Okay, so 6 different types of complexity I'm going to talk about. Although on here I've talked about time, I'm also going to be referring to space, because when we talk about the complexity of an algorithm, we're talking about 2 things: time as in how many operations there are, and space as in how much memory the algorithm needs in order to complete its operations. So first one is constant complexity. Either the time taken or the space needed to execute will always be the same. So the examples of this are things like checking to see whether a queue is empty. All right, it doesn't matter whether there's 100 items in the list or no items in the list. Checking to see if the first value is null or not is always going to take exactly the same amount of time. All right, similarly, if you want to push or pop an item from the stack, it's always going to take the same amount of time regardless of how large that stack is. Finally, in terms of space, if you're performing a bubble sort, the amount of extra memory you need in order to perform that operation is always going to be the same, because you only need one extra variable, i.e. that temp item, to hold one value while you're performing the swap during a bubble sort. Alright, the next one is linear complexity, where the time taken or the space, the amount of memory that is needed increases at the same rate as the input size is increasing. So therefore, example, this would be a linear search. Okay, when I have 10 items, it's going to take 10 operations. If I have 20 items, it takes 20 operations. If I have 25 items, it takes 25 operations. So as the input size is increasing, the number of operations are also increasing. All right, similarly, if you have an array, okay, you want to reset all the values in an array, or if you're making an array of objects or something like that, when you initialize each of those items, it's going to take the amount of time it takes is just linear in relation to the number of items in the input size. All right. Next one is the polynomial complexity. All right, or we talk about n to the power of k. So in this case, I've got n to the 2. What I'm talking about is when you have something like nested loops. Okay, because you have n items and you're performing n operations on those n items. Similarly, you can see if instead of printing ij, I was actually calculating and storing the value in a variable, then obviously the number of variables that I was going to have would be basically I times j. Okay, so here that's where we're talking about the polynomial rate. Basically, the more nested loops you have, the higher the value of the power of k. Okay, so if I have 3 nested loops, it will be n cubed, etc. Yeah. Now, when we can talk about exponential complexity over here, where each data item that we're adding to the input size is going to double the processing time. Okay, also could be doubling the amount of memory that is required. So this in the beginning doesn't seem to make much or have much of an impact, but then as the number of calls increases, all right, it just starts to balloon out of proportion. So an example of this is a recursive calls, for example, when the one that everybody used when they were learning recursion, which is probably a stupid way of learning recursion, but Fibonacci. So you probably remember when you wrote this algorithm when you were learning recursion and you coded it, and for a recursive call of like Fibonacci 10, it does it quite quickly, and then when you go to like Fibonacci 20, the computer takes forever. Okay, because each recursive call is doubling the amount of time that's needed. Now the next one, it's also doubling the amount of space that's required. Hence, you end up with a stack overflow quite quickly when you try to run Fibonacci like 200 or something like that, whereas you can run Fibonacci 200 quite easily if you're writing it iteratively. Now with factorial complexity, it's a bit more complicated. All right, if you want to think about, if you've got 6 people in your company, okay, and everyone sits at a different desk each day, so how many days is it going to take until they start repeating the pattern? Basically what you need to be able to do is to work out the number of, well, you need to enumerate all possible combinations, okay? So you need to know exactly how many permutations there are. To work that out, I'm going to do 6 times 5 times 4 times 3 times 2, because for the first desk I can put 6 possible people, for the second desk 5 possible people, for the third desk I've got 4 possible people, then for the fourth desk 3 possible people, fifth desk 2 possible people to sit there, and then there's 1 desk and 1 person left, okay? So in this case I know there's 720 permutations. So with factorial complexity, really what we're talking about is that the time that we need to run that algorithm is going to grow faster than the polynomial complexity because of the number of permutations. Where we see this are in examples like brute force searching, okay? So for example, if someone has a 6-letter password and they've used A to Z, and 0 to 9, so that's 26 plus 26 plus 10, 62 possible combinations, 62 possibilities per letter, okay? So if you work that out, 62 to the power of 6 is around, is it 50? I don't know. Where's my calculator? You can work it out yourself anyway, all right? It's quite a large number, okay? So here you can see when we start talking about encryption and password complexity, where why factorial complexity then it just vastly increases the amount of time needed to find a solution if you're going to brute force it. The last one is logarithmic complexity. You can go and find out about how logarithms work and this kind of stuff. My level maths is about 20 plus years out of date now. Alright, so basically what we're saying here is that the time and the space required to execute is basically going to plateau as the size of the data set that's been input increases, right? So basically an example of this would be like a binary search on a sorted data set, because basically if I have 1,000 items in my list, it's going to take me, was it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 possible operations in the worst case scenario to find my data item that I'm looking for, all right? However, if I had a linear search and I now suddenly, so if I now increase my data set to 2,000 items, it's only going to increase the number of operations by 1, all right? If I increase it to 4,000 items, it's increased by just 1 again. Compare that to a linear search. In a worst case scenario with 1,000 items, it could be 1,000 possible searches. 2,000 items, it's suddenly gone up to 2,000 possible searches, whereas with a binary search it was just 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 possible searches in a worst case scenario, okay? So you can see how the initial number of operations is the curve is steep, but it starts to plateau because it's a divide and conquer approach. So therefore we're saving operation time, okay? And the key thing here is to bear in mind is that a log n applies to divide and conquer approaches, okay? Now there are a couple of things to bear in mind with big O notation. First of all, when you're looking at an algorithm and you're working at its complexity, you take the largest possible factor into consideration. So it might be looking at n as well as n factorial, but then you just forget about the n because it's not that going to have that as much impact as the n factorial when you're looking at the complexity, okay? A couple of other things. Big O is worst case, all right? In a bubble sort, it's I've forgotten, it's n squared, okay? We're talking about so it's polynomial complexity because it's got 2 nested loops. However, if the list is already sorted, then it's only going to be big O n, okay, n complexity, because it's just going to go through the bubble sort. In that case, that sense is quite efficient because it triggers an escape quite quickly from the algorithm, from the sort, because it checks each time to see whether the list is sorted or not. So it's just going to iterate through the list once and then exit, all right? So big O does always go worst case. Moore's law, or in fact the guy, it wasn't Moore who said it, where the performance of a computer doubles every 18 months, right? It was like some other guy at Intel called David House who adapted what Moore said, right? And the upshot of that is that something that might have taken like a minute to execute 10 years ago might execute in a couple of seconds today. So like we talk about the complexity of an algorithm, but the knock-on impact in terms of performance in today's world sometimes, and I'm saying sometimes here, doesn't always have as big an impact as it would have had once upon a time. All right. Thirdly, speed can often be increased at the expense of using more memory in a computer system. All right. So you should be able to explain 6 big O classifications in relation to how they apply to time and space. You should be able to look at an algorithm and decide which one it falls into and what the impact on the execution of the algorithm is going to be. All right. And I'm gonna, still not used to this new bit of software, turn this thing off.